In this video here, we're going to take a look at trig identities. So let's just start with these two functions here. I got y equals cosine x and y equals sine x divided by tan x. Now I'm going to graph these two functions. So let's go to graph, and let's put in cosine x for the first one. And let's put in for the second function sine x divided by tan x. And I'm just going to make my view windows go from minus 2 pi to 2 pi. And I'm going to make this go a scale of pi over 2. I'm just setting it up for trig here. And let's go minus 2 to 2. And I'm just going to make sure I'm set up in radian mode. Excellent. Okay, let's graph them. So it's graphed both functions here, and it looks like the graph of y equals cos x and the graph of y equals sine x divided by tan x is exactly the same, because it appears like there's only one graph. So graphing them both again, they're exactly the same graph. So what I can presume then is that from my sketch that these must be exactly the same thing. So the cosine x, this expression right here, is exactly the same as this expression right here, because when I graphed them, they were exactly the same graph. And so what we're going to do here is we're going to look at how we can show that two trig expressions are equivalent. And if the two expressions are the same or equal to one another, then we can call that a trig identity. Let's consider this identity here. Supposedly tan x is equal to sine x times secant x. Let's say in the first thing here, the first thing we want to do is let's verify it is true for x equals pi over 4. Okay, so what I'm going to basically do is I'm going to put pi over 4 in for x here, here, and here, and that'll give me a number on the left side and a number on the right side, and I can see if they're the same for that x value. In order to do this, we're going to have to go back to our special triangles. So remember, this was the 1, 1, root 2 triangle. So let's see, the tan of pi over 4, we're going to see if that's equal to the sine of pi over 4 times secant of pi over 4. So the tan of pi over 4, that's opposite over adjacent, so that's 1. The sine of pi over 4 is opposite over hypotenuse, so that's 1 over root 2, times secant pi over 4. So secant is a reciprocal of cosine. So cosine, remember, is adjacent over hypotenuse. So secant ratio would be hypotenuse divided by adjacent. So hypotenuse would be root 2 divided by adjacent is 1. And just doing the work on the right side here to simplify this, 1 times root 2 is root 2. Root 2 times 1 is root 2. And root 2 divided by root 2 is 1. So we've shown that it verifies the left side and the right side of this identity are equivalent when x is equal to pi over 4. So we can't say it's true for all x values because we'd have to keep plugging them in. Try another one, try another one, try another one. And you don't have an infinite amount of time to try every single x value. So when we substitute it in for 1 point, all we can say is it is true for that 1 point. That's what's called verifying the identity for 1 point. So we've said it is definitely true for pi over 4. What we want to be able to do is we want to be able to prove that it's true for all values of x. So let's do that. So I've written the question here again. And we're going to prove that tan x is equal to sine x times secant x for all values of x, not just pi over 4. In order to do that, we need to look at some identities. And you've seen some of these things before. So there are some identities that you have seen. This is the reciprocal ones. And you know these things already, that cosecant x is the same thing as 1 divided by sine x. You know that secant x is the same thing as 1 divided by cosine x. And you know that cotangent x is the same thing as 1 divided by tan x. So you've learned those reciprocal functions already. So those are things that you know. You know that that's true. The other thing that you've learned, and these are called the quotient identities. You have learned that tan x is the same thing as sine x over cosine x, and therefore cotangent x, which is the reciprocal of tan, would be cos x over sine x. So these are things that you know already, and what we're going to do is we're going to use these identities to prove this one over here. So one of our first tricks in proving trig identities is to always convert everything to sine and cosine. So all of these expressions we can write in terms of sine x or cosine x. So here on the left side of my page, I've got tan x. Tan x is the same thing as sine x over cos x. So I can write tan x as sine x over cosine x. That's what I'm going to do here is I'm going to put a little dashed line down the page, because I'm going to work with the expression on the left side, and I'm going to work with the expression on the right side. So I've got my expression on my left side is sine x divided by cosine x. I've converted that side to sine and cosine. The right side I'm going to convert to sine and cosine. So this first one is already in terms of sine x, so I'm going to leave that. But secant x, here's the identity right here. Secant x is the same thing as 1 over cosine x. So I'm going to write secant x as 1 over cosine x. And now sine x is the same as sine x over 1 as a fraction. So now I can multiply these things together. Sine x times 1 is sine x, and 1 times cos x is cosine x. So we've now shown that the left side is sine x over cos x. The right side is also sine x over cos x. So we have proven that the left side and the right side are identical, because the two expressions look exactly the same now. So that's how we would prove that for any value of x, tan x would be equivalent to sine x times secant x. Now, of course, there's some values of x that won't work in this expression because we have a fraction here. So sine x divided by cosine x, we know that we can't divide by 0. So that means that cosine x cannot be 0, because if I divide by 0, this identity is going to be a problem. So if you remember back to your cosine graph, which looks like this, we have some non-permissible values, because there's some places on here where cosine x would equal 0, namely pi over 2, 3 pi over 2, 5 pi over 2, and so on. So our non-permissible values are x could not be pi over 2, and if we continue to add pi, we would keep hitting these additional x-intercepts. So our non-permissible values are x cannot be pi over 2 plus any multiple of pi, so plus n pi, where n is an integer. So we can't take pi over 2, we can't add 1 pi to it, or 2 pi, or 3 pi, or minus a pi, or minus 2 pi. These would all give us values where cosine of that number would be 0. So we can't divide by 0. So cosine x, there's the cosine graph, cannot be 0. So x cannot be values like pi over 2 plus n pi, where n's an integer. Otherwise, any value of x on the left side will equal any value of x on the right side. Let's look at the identity sine x divided by tan x equals cosine x. So the first thing I'm going to do is put a little line down the middle of my identity here. I'm going to work on the left side, and I might work on the right side. Although if my step is to convert everything to sine and cosine, I don't need to do any work on the right side because it already is in terms of sine or cosine. We just have cosine x. So the only thing it looks like I've got to do on the left side here is get rid of this tan x. And our identity for tan x is that it's sine x divided by cosine x. So tan x is sine x over cos x. And so now I have sine x divided by tan x, which is now sine x over cosine x. So everything is in terms of sine x and cosine x. Now we just got to tidy this expression up. Well, I've got sine x divided by a fraction. So we just got to review this. If we had 5 over 2 divided by 3/4, remember, to divide fractions, we multiply by the reciprocal. So change it to a times sign and take the reciprocal of the second expression there. So I'm going to do the same thing. I got sine x divided by this, so that would be the same as sine x times the reciprocal, which is this. And then sine x is like sine x over 1. So up top in the numerator, I'd have sine x times cosine x divided by 1 times sine x, which is sine x. And hey, sine x divided by sine x is 1. So I just have cosine x. And now the left side is equivalent to the right side. Let's look at our non-permissible values for this one. So what are the values of x that wouldn't work? Well, we go back to the original expression and we say, okay, sine x divided by tan x, so tan x cannot equal 0 because we can't divide by 0. Well, and again, if we look at our tan graph, where is tan x equal to 0? Here, here, so tan x equals 0 at 0, pi, 2 pi, 3 pi, 4 pi. So x cannot equal any multiple of pi, where n's an integer. So 0 is not going to work, because if I put 0 in for x, the tangent of 0 is 0, and this divided by 0 is not going to work. So x can't be these values. But then tan x itself is not defined at pi over 2. So if I put pi over 2 in for x, the tangent of pi over 2 doesn't exist, because there's an asymptote there. So other non-permissible values are pi over 2, and then those asymptotes also occur every pi units. So x cannot equal pi over 2 plus any multiple of pi. Those are the values that would not work in this identity. This one, because when we put any multiple of pi in for x, the tangent of that is 0, and we can't take sine x and divide it by 0. This one, these values don't work because tan itself is undefined at pi over 2 and 3 pi over 2 and so on. Let's find some other identities that are useful to us. Let's say we've got a unit circle here. So this is x-axis, y-axis, and let's say we've got a radius of 1 to here. So this is a unit circle, radius of 1. Well, if I drop a perpendicular down to the x-axis, then I know that this distance along here is going to be cosine x. And this distance up here is going to be sine x, because this point is the point cos x, comma, sine x. And why is that? Well, because cos x is always equal to adjacent divided by hypotenuse. And so if this is my angle theta here, this would be the adjacent side, and this would be the hypotenuse, 1. So if I want to know how long is my adjacent side, then adjacent would just equal, if I multiply both sides by the hypotenuse, gone, I would get cos x times the hypotenuse. And how long is the hypotenuse? The hypotenuse is 1. So the adjacent would be cos x times 1, which is just cosine x. So the adjacent side is cosine x. If I wanted to find the opposite side, well, sine theta equals opposite over hypotenuse. So sine theta equals the opposite side divided by the hypotenuse, which we know is 1. So opposite equals sine theta. Or I was using x here, so sine x. So this would be a triangle with the radius of 1. So I'm just going to pull that triangle out here. So this side's 1. This side's cos x. This side is sine x. And this is a 90-degree triangle. So Pythagoras would say that cos squared plus sine squared equals the hypotenuse squared. Well, 1 squared is just 1. So this would be a new identity. Cos squared x plus sine squared x equals 1. And if we were to graph it, so bracket cosine x, the calculator, you got to enter it like this. It doesn't work if you go, it won't work if you do this, cos squared x. Okay, it doesn't understand that, so you got to go bracket cosine x squared plus sine x all squared. And when we graph this, this should equal 1. There we go. We got a line at 1. So for any value of x, you're always generating a y value of 1. So these are another identity. So these are our Pythagorean identities here. Cos squared plus sine squared equals 1. That's the one that we just showed. These other ones you can generate in a similar manner from the graph, from the triangle. So 1 plus tan x squared equals secant squared x, and cotangent squared x plus 1 equals cosecant squared x. So let's look at this one here that we have to prove. 1 minus cos squared x equals cos squared tan squared. So anytime you see something squared plus 1 or minus 1, think of these identities here. So 1 minus cos squared. I'm looking at this first one here, and I'm thinking if I took this cos squared x and brought this over to the other side, so let's just do that down here. So if I minus cos squared x from both sides, gone, this identity would now look like this. And so 1 minus cos squared x is sine squared x. So I can say on the left side that 1 minus cos squared is sine squared x from this identity. On the right side, I'm going to get everything sine and cosine. So tan x is sine x divided by cos x. So tan squared x would be sine squared over cos squared. So convert everything to sine and cosine. This is a 1, so numerator is cos squared x times sine squared x divided by 1 times cos squared is cos squared x. And now these conveniently cancel each other out. Cos squared divided by cos squared is 1. So we have sine squared x. And now the left side equals the right side, so that identity has been proven. Let's look at this last example here. Cosecant squared x minus 1 equals cosecant squared x times cos squared x. Well, here's one of these something squared plus 1 minus 1 things. So I'm thinking maybe one of those Pythagorean identities. Let's see, cosecant squared minus 1. This is the one here. Let's just copy this down here again. So cotangent squared x plus 1 equals cosecant squared x. I need to get cosecant squared x minus 1. So if I were to minus 1 from both sides, the identity would look like cosecant squared x minus 1 equals cotangent squared x. Put the little line down between the two. Now I need everything in terms of sine and cosine. So on the right side, cosecant x is the same thing as 1 over sine x. So this would become 1 over sine squared x, because it was cosecant squared x, times cos squared x. That's fine, but that's over 1. So in the numerator I have 1 times cos squared x, which is cos squared x, and in the denominator I have sine squared x times 1, which is sine squared x. And so that's about as simple as it gets on the right side. Everything's sine and cosine. And well, the left side is not. So the left side is not in terms of sine and cosine. So another identity to use here. Cotangent is cos x over sine x. So cotangent squared would be cos squared over sine squared. And yeah, we have the left side the same as the right side, so we have proven that identity.